Welcome to a brief introduction to mechanical ventilation. This is chapter 1.2, oxygen. Now here's a fun fact. Did you know that breathing, the act of actually moving your lungs in and out, actually is not necessary for oxygen exchange to occur? We know this because we do a test called an apnea test when somebody is brain dead, where we have them on a ventilator, we disconnect them from the ventilator, and just with the endotracheal tube attached to 100% oxygen flowing across it in a T-piece, we can see that the oxygen saturations never change even though the patient is not taking in breaths. This occurs because there's diffusion of and a gradient for oxygen flow from the end of the endotracheal tube down to the alveoli, and then just diffusion alone is sufficient in order to allow oxygen exchange to occur. When you take all of the alveoli and spread them out and measure their surface area, an average person's lungs encompasses an entire tennis court in surface area. So you can see that there's actually a very large surface area in all of us for oxygen exchange. And so therefore, this allows us to have the buffer of using diffusion alone in order to maintain adequate oxygenation. There are two ways in which oxygen is transported to the cells. First, and by far the most common, is having it bound to hemoglobin molecules inside each of the red blood cells. Second way is to have it dissolved directly in the blood, just like you would see when you open a can of pop and you see the bubbles forming. This is carbon dioxide that's dissolved in the pop. Much of the same thing happens in the blood, where oxygen gets dissolved into the blood itself. Now we can actually measure the amount of oxygen that is being delivered by calculating the oxygen content of blood using this formula. And then if we combine this with the cardiac output, we actually have on top of that the total oxygen delivery, which in critical care is an important thing for us to be able to measure. As you can see from the formula, the amount of oxygen dissolved in the blood is actually a very small component of the total amount of oxygen that is delivered to the cells. The reason we measure both of these together is because there's a relationship between the oxygen dissolved in the blood, the PO2, and the oxygen saturations, and this is expressed in the oxygen dissociation curve that you can see here. You can see that there's at a certain level of PO2, the oxygen saturations are a certain level, and this is mostly related to the binding properties of hemoglobin itself. As the PO2 goes down, oxygen saturations start to fall off much more rapidly. So the amount of oxygen that being delivered by the hemoglobin is by far more important. We measure the PO2 more or less as an early warning that there is going to be a problem with the oxygen saturations. So a low PO2 shouldn't necessarily make one panic, but make them watchful that the oxygen saturations are going to start to fall off. There are 5 things that can cause hypoxemia. The first mechanism is hypoventilation. Now, the alveoli is a gas-filled space, and when one of the constituent parts of the gas, whether that's nitrogen, oxygen, or CO2, goes up, then there's only a certain amount of room and the concentration of one of the other gases has to go down. When somebody is hypoventilating, the continuous delivery of carbon dioxide and the concentration gradient into the alveoli from the blood of carbon dioxide raises the alveolar concentration of carbon dioxide. This elevation necessarily causes a decrease in the amount of oxygen in the alveoli, and by doing so decreases the concentration gradient for oxygen from out of the alveoli and into the blood. Hypoventilation will typically cause an elevation in the CO2 a lot earlier than you would see a fall in the oxygen levels. A clue that hypoventilation is the cause is on an arterial blood gas. You see that the CO2 is very elevated, and when you give them a little bit of oxygen, the hypoxia goes away. The second mechanism is VQ mismatch. Now we're going to talk about VQ and mismatch in a lot more detail in subsequent sections. But for now, just understand that there's a mismatch between the amount of oxygen in the lungs versus the amount of blood being delivered to the lungs. And if there's not a good match between the amount of air being inspired and the blood flow, then the transport and gas exchange becomes a problem and the oxygen levels can decrease. The third mechanism is what's called a right-to-left shunt, and this refers to blood shunting from the right side of the heart, so from the right ventricle, directly over onto the left side, or the left ventricle. A right-to-left shunt occurs when the blood shunts from the right to the left side without being oxygenated. There are two types of right-to-left shunts that you should be aware of. The first is an anatomical shunt. The alveoli are completely bypassed. You can see this when somebody has an intercardiac shunt, such as a hole in the heart that's causing blood to flow from the right side to the left side, or when there's a shunt within the pulmonary vessels, such as when there's what's called an arteriovenous malformation or hepatopulmonary syndrome. Physiological shunts can occur whenever there's blood flowing across non-ventilated alveoli. This type of shunt we will also talk about in a lot more detail in a subsequent section. The fourth mechanism is diffusion limitation. Now we talked in the previous section about the interstitial space, and in some cases, such as with pulmonary fibrosis, this space, which is usually very thin, can actually become very thick. And since oxygen diffuses across a concentration gradient and there's actually nothing to drive oxygen or transport oxygen, this increased thickness can decrease the amount of oxygen that can diffuse into the blood from the alveoli in the time necessary from the blood to pick it up and transport it. The final mechanism is reduced inspired oxygen tension. The pressure gradient for oxygen flow is related to the atmospheric pressure as well as the fraction of oxygen, or FiO2. In some circumstances, if the atmospheric pressure decreases, the amount of available oxygen pressure to drive diffusion goes down significantly. This is a consequence of altitude for the most part and generally is not a cause of hypoxia or hypoxemia when somebody is being initially assessed. This is relevant, however, whenever you're trying to transport somebody at a high altitude. So today we've talked about the exchange of oxygen. We've discussed how oxygen is transported, both dissolved in the blood and bound to hemoglobin, the relationship between the PO2 and the oxygen saturations, as well as the 5 mechanisms that cause hypoxemia, including hypoventilation, VQ mismatch, right-to-left shunt, diffusion limitations, and decreased in partial pressures of oxygen.